Where's my mouse? Oh, it's up there. All right, let's do these two. So the 51, 52. This is college people work. It should give us a good idea of what's going on. It's not March yet.
Tomorrow.
It is tomorrow. It's like,
oh, today's leap day.
Yeah, today is leap day, which was kind of screwy because I got up to do my Bible reading. It's like, wait, my Bible reading schedule doesn't have a February 29th on it. It's like, what do I do? All right, so there's currents in the same direction. Find the direction of the magnetic field at P1 made midway between the wires. Okay. So we could look at the equations and like work this out. I really don't want to. So maybe we're supposed to actually go ahead and cover Ampere's law now. I don't know. We'll see if they ask us to actually find it. They said midway between the wires. Okay, there. I guess we are supposed to go ahead and cover Ampere's law. Well, let's do the first part anyway. So this is another version of the right-hand rule. We're going to see in just a second that the magnetic field for if you have an infinitely long wire, put your thumb in the direction of the current, then the magnetic field wraps circles around the wire and it goes in the direction of your fingers. So like that wire is coming out of the board, so these magnetic fields from both of them are going counterclockwise.
Yeah, but right in the middle of them, it's going to even out the left, right?
Well, it's just saying from the direction of the magnetic field. Yeah, midway between the wires is you're going to have the one on the left. If you go counterclockwise, it's going up. The other one's going down. So that one's going to be 0. So that one was easy. Boom. What's the magnetic field at P1? 0. Boom. Okay. If I go at P2, which is 29 centimeters to the right of P1, so we're looking like 25.
That's the second one, right?
Yes. No. Wait. It's
which one's P1 and which one's P2?
P1 is right in the middle. So 29 centimeters.
Are you saying
so 24 centimeters, but neither one of the wires are RPs. So 24 centimeters past that second wire is where we're wanting to look. Okay, so again, both magnetic fields are going counterclockwise. If I look way out to the right, well, they're both going up over there. So it's gonna go to the top of the page. All right, find the magnetic field. Okay, so we need to figure out what's the magnetic field of an infinitely long wire. To do that, we have Ampere's law. So let's talk about Ampere's law just real quick. I'll go ahead and tell this for Colby's sake. If for some reason you ever find yourself in an upper level electromagnetism class, I don't know that you probably will, and I'm not sure. Engineering's kind of different. It's like there's the old joke. It's like a physicist, a mathematician, and an engineer are all given the problem: find the volume of a red rubber ball. The physicist drops the ball in water, sees how much the level goes up, finds the volume. The mathematician does a triple integral, computes the volume. The engineer looks up the make and model of the red rubber ball in his red rubber ball guidebook.
Yeah.
It's like, so, but anyway, I mean, the point is like, so this cross product or whatever, I mean, the D is like the direction of your current. The R is wherever you want the field from. So if I wanted to know this whole wire, well, I mean, you have to do an integral. And what makes the integral tricky is that this angle between where you're at and the point where you're trying to find the field is changing the whole time, which, I mean, basically just means these are a pain in the backside to actually do. So anyway, that's all you really, oh, I went away. And so did my hats. Okay. So that's really all you need to know about Biot-Savart law, is that we're not going to use it. We're going to use Ampere's law, which, just like we did with Gauss law, I mean, if you know the Ampere's law, you can derive Biot-Savart law, vice versa. If you know a lot of math and you know Biot-Savart law, you can get Ampere's law. So Ampere's law says if I have a closed curve, so Gauss law, we had a closed surface. Ampere's law, we're just going to draw a little curve. If you go, again, this isn't going to make any sense to Cindy, but that's okay because I'll tell her what it means in a second. B dot dl. This is mu naught times I enclosed. So this is a path integral. It's basically, so if you pick out the curve so that the magnetic field is constant, this is just B times length times the cosine of the angle between the B and the curve. So for the example we care about, if I have an infinitely long wire with current I, well, I draw my curve going around the wire. And again, you kind of have to work this out with Biot-Savart law the first time, but it's like the B is going to go in circles around the wire, and it's constant on that radius or whatever. So as far as anyway, this is just B times the length of that circle, which is 2 pi r for that side. And then on the other side, you got mu naught I enclosed. So the magnetic field for a infinite wire is just mu naught I over 2 pi r, which is actually surprisingly similar to the electric field for an infinite line of charge. But, I mean,
question.
yes.
You did up there on Ampere's law.
Mm-hmm.
It was anyway. The example the deal NEI and then it's like ENC.
Yeah, the ENC means enclosed. So it's like your curve is, it's just like Gauss law or whatever. If there's no currents inside of that loop, then that integral is going to be 0.
Okay.
But if you have currents, and you have to pick a sign. I can't really remember the sign, so you use right-hand rule at the end of the day. So, but like if you've got currents going 2 directions, like say if I did the magnetic field of, well, let's say y'all can't see it. The bottom part of this cord, like underneath the transformer. So if you've never actually stopped, and you can't really see it as well on modern cords. On older cords, there was a very distinctive dip in between. That's because there's a wire running both ways, right? I mean, you've got to get electricity to the thing, but in order to have a closed circuit, you have to get it back. If I do the magnetic field around this while there's juice running through it, it's 0 because the 2 currents are the same and they're going in opposite directions. So, yeah. So you have to pick one direction as being positive, one as being negative. If you wind up getting a positive magnetic field out of it, that means the one you picked positive, do the right-hand rule around it. If you get a negative magnetic field, do the right-hand rule around the other one. And if you're ever teaching this class and you're working with someone at office hours and they're sitting on your left, there was one time I got completely, it's like we were getting the right number for the magnetic field, but it was going the wrong direction every time. The reason was because the student was sitting here, I was pointing to her screen with this hand and trying to do my right hand rule with the left hand. It doesn't work.
Might make a difference.
So. All right. Okay, so if we're 29 centimeters to the right of P1, so we decide that's 24 centimeters to the right of this guy, which would make it 34 to the right of that guy. So all we're going to do is use this formula we just got. If I can get the thing to move.
It works good. Do you really need it?
Exactly. There we go. Okay, well, since it's not moving, let's just rewrite it. Oh, see, there we go. Okay. Mu naught I over 2 pi r. So we're going to have r as 0.24 and r is 0.34. And we decide they're both going up, so they're going to add together. So what was I? They're both carrying 5 amp currents. So let me do the over r's first. So I've got 0.24 plus 0.34, that, and then I've got times mu naught, which is 4. Well, mu naught is 4 pi times 10 to the minus 7, so mu naught over 2 pi would be 2 times 10 to the minus 7. So 2, and then times 5, and then there's times 10 to the minus 7th, so 4.75 times 10 to the minus 6, if I typed in my calculator right. Which is pretty small. No, I did not type into my calculator right. Let's try this one more time. So I is 5. And okay, let's do the whole thing. So 5 times 2 divided by 0.24 is that, plus 5 times 2 divided by 0.34 is that. And then that's not at all what I got the first time, is it? So let's try 7.11 then.
So what did you just do there when you cut it down with the 5 divided by?
Okay, so again, the 5 is the current. Mu naught over 2 pi. Well, mu naught is 4 pi times 10 to the minus 7th. So this is just 2 times 10 to the minus 7th.
Okay.
So I did 5 times 2 divided by r for both of them added together.
But in longhand, it'd be 5 times 2.
Yeah, which I did the e negative 7 at the very end because
I'm with you.
I hate this calculator. All right, cool. So the next one was difficulty 3. So we're not going to fear. We're confident that we can do it. So 2 long parallel transition lines, 43 centimeters apart, carry that and that. Find all location where the magnetic field of the wires is 0 if the currents are in the same direction. Okay, so this is actually not hard. It's just algebra. I mean, the physics is not hard. It's just algebra, right? So we're going to basically draw the same. So 43, 21.5, and 71.5. And again, when you've scrolled a certain distance, it doesn't want to scroll anymore. So this guy is 21.5. This guy is 71.5, was it? And they're 43 apart. Yes. Okay. And it says make X the distance from the 21.5 wire. So I want the magnetic field right there to be 0, which, so it says both currents are going in the same direction. So it's just like the last one. The magnetic field coming from the 21.5 guy is going to be going up. From the 71.5 is going to be going down. So in the middle, they can actually cancel. If you went off to either side, though, like if you went past the 71.5, they'd both be going up. If you went on this side, they'd both be going down. So the only way they can actually cancel each other out is if we're somewhere in between like that. All right. So if we're in between, though, they will cancel each other out if they're equal to each other, right? So we've got mu naught times 21.5 over 2 pi x needs to be mu naught times 71.5 over 2 pi. How far is this point from the 71.5 guy?
Be 43 minus X.
Yeah, 43 minus x. Right. So the mu naughts over 2 pi's cancel out. I've got 21.5 times 43 minus 21.5x equals, if I'm cross multiplying is all I'm doing, 71.5x. Add that to both sides, so 21.5 times 43, 71.5 and 21 is 93.
Aren't you missing an X?
Am I missing an X?
Well, you got 21.5 times 43, but what did you do with that minus X?
Okay, that's this one right here. I mean, so when I cross multiply, this guy will distribute. You'll go 21.5 times 43 and 21.5 times minus
okay,
X.
Okay,
right. Okay. Let me not write times like that. It just bugs me. And then when we move this guy to the other side, it'll become plus. So 21.5 and 71.5 is 93. And then divide by 93. So 21.5 times 43 over 93.
I had a
9.94.
dot because if I could do the multiplying,
Yeah.
I'll give myself confused.
Yeah, I don't know why I wrote that.
If I look up for just a second, I'd be like, go back. Oh, you're going in there anyway.
Okay. Yeah, okay, got it.
Work.
Right. We're about to go back to the work. If they're going in opposite directions, and then the first one's going to be from the 21.5, the second one from the 71.5. Let's just do one of them because they're really exactly the same. But, I mean, they're a lot like the first part. But, so you happy with my work, Colby?
Yeah. Just making sure that I saw what you did.
So let's redraw the picture. 21.5 and then 43 and 71.5. Okay, so one of them's going out of the board, one of them's going into the board. So the 21.5, at least the way I drew it, the fields are still going counterclockwise. The 71.5, the fields are going clockwise. So now in the middle, they're both going to be going up. So the net field is always up in the middle. If I go out past the 75, the 21.5 guy is up. Yeah, but the 71.5 guy is down, right? If I go out past the 21.5 guy, the 21.5 guy is down, but the 75 guy is up. So can you tell me on which of the two sides could we possibly have a zero magnetic field? It's not going to be in the middle because in the middle they combine together, but they're going in opposite directions on either side. So is it going to be over here on the left or over there on the right?
We're still carrying the same amps, right?
They're not carrying the same amps. That's the important part. One of them's carrying 21.5 amps, the other one's carrying 71.5
Okay.
amps.
It's gonna be towards the left.
Yeah, it's going to be on the left because on the right, well, there's kind of two things going on. I mean, you've got these two magnetic fields that are fighting each other, but the one coming from the 71.5, it's closer, so it's bigger, and the current's bigger, so it's bigger. So it's always going to win. But over here on the left side, well, the 21.5 is bigger because it's closer, but the 71.5 is bigger because it's bigger, because the current's bigger. So there's a chance on the 21.5 side it could actually cancel out. Right? Okay. So now that we've done all of our talking, the math is like almost the exact same as the last one. So we're just going to do our X over here. Well, the guy coming from the 21.5 is 21.5. Well, mu naught times 21.5 over 2 pi and then X, right? So, why not? I'll write the mu naught over 2 pi, even though it's about to cancel out. And then same thing from the other one, 71.5 mu naught over 2 pi. And the only difference is now we have 43 plus X. Right? So again, the mu naughts cancel. Again, you cross multiply. So we got 21.5 times 43. But this time it's plus 21.5X is 71.5X. So subtract, that gives me 50. So 21.5 times 43 over 50 is my X. So we're 18.5. It says, okay, it wants the distance from the 21 guy first. It also wants the distance from the 71 guy, which, well, it's just that plus 43. So 51.3. No, 5. Wow. That's pretty, oh, no. At 18.5 plus 43. Oh, that's it. It's 61.5. Hey, I told Cindy first thing, it's like, this is the least Friday-ish morning I think I've had in a long time.
Don't feel bad. I was sitting there Friday night. I told